So today we are going to learn about program design. So this is again under design part, and that we already learned planning, analysis. We are still in design. Logical DFD into physical DFD. So today's learning objective, we are going to structure chart, program specification, pseudocode, event-driven programming. So we are going to learn these items. Moving from logical to physical process models. What is physical process models? That show the implementation details and explain how the system will work, including actual technology, specific technology, format of information, human interaction with the system. So basically, physical process model is on the top of DFD, that explains how these logical structure, how these logical interlinks will be used using what technology, like HTML, like database technologies or different user interface. So physical DFD that contains the same component as a logical DFD. So we learned DFDs 0, 1, 2 in the previous class. On the top of that, we are just going to see how these technologies, how these logics, or how these flow, and how these flows will work using what technology. So this is what is physical DFD. Additional detail describing how the system will be built, which is physical DFD. So what are the steps to create the physical DFDs? Add implementation reference, that how data stores, data flows, processes are implemented. Draw human machine boundary, separate human action from automated process, means this is very important, where human is going to interact with machine. Add system related data stores, data flows and processes. Update the data flows with additional physical data elements, for example, system generated IDs, and update the metadata in the case repository. So this is a very good representation. You can see, can you see this is, for example, you already made this, this thing in DFDs. Now this is a physical DFD. What you are going to see, this dash line, this is human part, marketing managers, customer, this is the, this dash line is separating human, and then this is machine or, computer or automated processes. Look into the marketing managers, sales patterns reports, he gets sales pattern reports from promote tunes, promotion decision, input form, this is, for example, this is the form of report, this is in the form of forms, and for example here HTML email is used in this to input to and promotion message, customer gets in the form of HTML, in the form of email. So this HTML and email technology is used here. Look into promotion or promote tunes, Visual Basic, technology is used. Time to determine promotion, here access report, email messages are there. Look into this D4, D5, D3. This is MySQL record, customer interest, recent sales, MySQL record, sorry. Here also you can see MySQL record, new websites promotion, so MySQL field. So this is an customer email. So basically here this is logical flow or logical DFDs. This is a physical, means what technology will be used to facilitate or to make this, logical DFD into practice or into working. So these technologies, so and this reference line is, this is the boundary where human is interacting with the machine. So it should be very clear what is the difference between logical DFD and physical DFDs. Designing programs. Now after that, program design is creating instructions for the programmers. The top-down modular approach is beginning with the big picture and gradually add details. Program design document all structure chart and specification needed by programmers to implement the system. So basically, this is the program design documents that include structure charts for needed for programmers to implement the system. And it is big picture, and gradually add the details. So basically program design is about, instructions for programmers to implement the system. It has a structure chart, and this is an important technique in design a program. It includes all components of code at high level in a hierarchical format, and the component are usually read from top to bottom, left to right, left to right always. Top to bottom and left to right. So this is called, you can simply understand the structure, hierarchical structure, hierarchy top to bottom and left to right. Look into this, an example of a structure chart. Here you can see create students grade listing. And here you have these 4 components. So this is 1, 1.1, 1.2, 1.3, 1.4. Here you can see get students grade record, calculate current GPA, calculate cumulative GPA, and display grading listing. Here you can see students grade record is going into create student grade listing, end of file. And what is coming here, calculate current GPA, grade record. So, and current GPA is going up. You can see this, I'm going to explain the meaning. And in the display grade listing, what is coming in this? Student SSN, student name, cumulative, current GPA, all is going to be display into display grading list, grade list. Here you can see calculate cumulative GPA, grade record is coming, but what is going here from here, cumulative GPA. So this is an example of a structure chart. The structure chart, composed of modules, couples, connection lines, and connectors. So modules are lines of programs code that perform a single function. What is modules? That includes lines of program code that perform a single function. And here 3 types of modules: control module, a higher level component that contains the logic for performing Other modules, subordinate module, a component that is called by control module, and a component that is standardized and used in many places throughout the system, which is library module. So these three modules are there. We are going to see and this is connection lines, loop curves. You can see this is a loop from right to here. Conditional lines, which you can see here. How connection line, how communicate the passing of control. So here you can see on page continuation and new parts, and connectors to connect extended parts of a structured chart. So these are now here are the symbols. So these are a data couple, a control couple, an off-page connector, an on-page connector, and here you can see every module, every library module. Here you can see a loop and a conditional line. So these are the symbol, or these are the interpretation of all the elements in the structure chart. What is the meaning of the data couple, which you can see the arrow? Grade record, for example, end of file. So grade record contains an arrow, contains an empty circle, names the type of data that are being passed, can be passed up or down, has a direction that is denoted by the arrow. So how the data is going, that is being denoted by this. So the difference between control and data couple, here you can see contains an arrow, contains a filled in circle. So at the back you can see which is filled circle here, names the message or flag that is being passed, should be passed up, not down. Always should be passed up, not down, has a direction that is denoted by arrows. So basically, it has a direction. And this communicate that the message or system flag is being passed from one module to another module. So you can just look into this. So grade record here, it is going end of file. So it has both the both the arrow, which one is circle is filled and circle is empty. Here you can see, and other places we don't have such things. So please make sure to distinguish between data couple and control couple. And an off-page connector is denoted by a hexagon, has a title, is used when the diagram is too large to fit everything on the same page. When diagram becomes very large and it is difficult to fit everything on a page, then we use. And identifies when parts of the diagram are continued on another page of the structure chart. So print grade listing, for example, here on this, on 1.4, this is display dean's list, display grade listing. An on-page connector is denoted by circle, has a title, is used when the diagram is too large to fit everything on the same spot of the page. And this is identifies when part of the diagram are continued somewhere else on the same page on the structure, and therefore it is denoted by circle with heading or title, sorry. And then we come here. And this is every module has a number, has a name, is a control module if it is a control module if it calls other modules below it, is subordinate module if it is a controlled by module at a higher level. So denotes a logical place of the program. So basically here you can see the symbol 1.2 calculate current GPA. Every library module has a number, name, multiple instances with a diagram. For example, denotes a logical place of the program that is repeated with the excuse me, that is repeated with the structure chart. And here you can see 1.1 get student grade record. A loop is like this, is drawn with curved arrow, is placed around lines of one or more modules that are repeated. So remember, this normally this people do wrong, instead of this direction, that direction communicates a module is repeated. So here, and then conditional line is drawn with a diamond, includes modules that are invoked or basis of some conditions. So basically here you can see communicates that subordinate modules are invoked by control modules based on some conditions. So here you can see these are the 8 symbols that we have to keep in mind for doing the assignment also for this week. And here, now you can understand this chart very easily. This is structure chart. What is the meaning of these lines? End of file. What is the meaning? Because this end of file can be only of Word. The grade of students or students grade record, these lines which without filled circle, they can be up and down. So building the structure chart, a DFD process, a structure chart module, a DFD level, a structure chart level, and context diagram, the top structure chart module. And in the structure chart, there are 3 basic kinds of processes are there. Afferent processes, central processes, and efferent processes. The first one, afferent process provide inputs into the system. Central processes that perform critical function in the operation of the system, which we can simply and deal with the system output. So these are the input, process, and output, which we can simply understand in any system. These are the 3 basic components. And then transaction structure, that control module calls subordinate modules, each of which handle a particular transaction, has few different processes, has many different processes occur high up in the level of a structure chart, and concerned with coordination of modules to produce output. So example of transaction structure, here you can see student grade system. Here you can see this diamond is here. That means all are going to be, cannot fit on one. Maintain a student grade, maintain a student, generate individual grade report, display student grading listing. So these are the structure chart types. Transform structure, and that control modules cause several subordinate modules in sequence, each of which perform a step in a process that transform an input into output. Has many different afferent processes, has few efferent processes, occurs low in the level of structure chart and concerned with using inputs to create new output. So look into example of transform structure here. The same thing, same, but here you can see the loop. Loop you can see here. Types of structure chart, high level DFDs, which is transaction structure, and low level DFD, so transform structure. So you can clearly see these are the situations. Steps in building a structure chart, because you have to do a structure chart this week assignment. Identify top level modules and decompose them into lower levels. So basically hierarchy you can understand. Add connection line, add couples, data or control, and review and revise again and again until it is complete. So basically first thing you have to break into hierarchy, add connection line, add couples, and review and revise again and again until it is complete. So these are the 4 steps in order to do a structure chart. And then design guidelines are high quality structure charts results in program that are modular, reusable, and easy to implement. That measures include cohesion, coupling, fan in and fan out. What are those? What is cohesion? How well the codes within each module related to each other, like ideally each module for one task. How closely modules are interrelated, should be loosely coupled. Connection to and from a module, not low fan in to be reused by many and not fan out to be manageable. So here, types of cohesion you can see in this. Functions, sequential, good, and here you can see good to bad. So this is function to coincidental. This is going from good to bad. This is the definition, and this is an example of each of them. So functional module performs one problem related task, calculate GPA. Sequential output from one task is used by next. Communication, elements contribute to activities that use the same inputs and output. Procedural, elements are performed in sequence but don't share data. Temporal, activities are related in time. Logical, list of activities which one to perform is cohesion. Outside of module, and coincidental, no apparent relationship. So basically, you can see this good to bad. This is a type of cohesion. So basically, and here these are the examples which you can see. Types of cohesion, this is the best. Does the module do one thing? And if the answer yes, functional cohesion, that is, know how are the tasks related. So this is the best option. If no, you can say, you can go further. Here, how are the tasks related? Data, sequence important. Flow of control is sequence important. Neither are the tasks related to the same general category. So here again, you can say this is from good to bad. So this is, good. This is, this option is bad. Here is moderate. So basically, this is a cohesion tree, cohesion decision tree, and that explains and, makes where you have the best things. So basically, uh, if module has one thing, that is the best thing. If the tasks are related, and then then you have to go through the decision tree and see which is the best option, or which is the good choice. So here you can see the type, the same types of cohesion, good to. Again, one more thing, which is factoring. Process of dealing with low cohesion and separate tasks into different modules, reduce use of control flags. So design guidelines, how quality structures, charts result in programs that are modular, reusable, and easy to implement. Cohesion, coupling, and fan-in, fan-out, which we have just seen. I mean, these are the three measurable, include cohesion, coupling, and fan-in, fan-out. Types of coupling. Here you can see data, how data is going from where to where, module pass field of data or message. So here this is a student ID, and we have just seen this is a data coupling. All couples that are passed are used by the receiving module. So a stamp, and then after data, here good to bad again. Module pass record structure. Not all of the student record is used by receiving module. Only the student ID field is. So here, for example, student record, current GPA. Update students record, and here calculate current GPA. So this is, in first case, all couples that are passed are used by receiving modules. Here, the control, you can see, module passes a piece of information that intends to control logic. Here you can see in this case, update students record, student ID, and current or cumulative GPA. Current or cumulative flag. So this is, the file goes here, and here calculate current or cumulative GPA. So this file, the receiving module has to determine which GPA to calculate. So control common modules refer to the same global data area, that is. So here common and content module refers to the inside of the another module. For example, you can see the last one, content, module A, update students. If student equal to new, then go to module B, create a student, all the cost, avoid modules. So such conditions are, in coupling is considered bad. The best thing is, so from top to bottom, you can see. So if you have logic, if you have, inside another module, which you can see clearly in content, that considered not good. And these are some of the design guidelines. High quality structure chart results in programs that are modular, reusable, and easy to implement. Cohesion, how well the course within each module related to each other. Coupling, how closely modules are interrelated. And fan-in, fan-out, connection to and from a module, not low in fan-in and not high in fan-out. So basically, again, these are, so fan-in and fan-out. So high fan-in, here you can see that means 1, 2, 3, 3 are just, which is many, submodules are, sorry, so for example, reuse of subordinate modules. So here you can see high fan in, and here you can see low fan in, only 1 to 1. Here many to 1. And here you can see fan out. So how, one to many. So fan in and fan out. So basically the principle is that not low fan in and not high fan out. Means this situation shouldn't be there. I mean, we can't, mitigate, but if this is the situation, this and high fan out. So some of the points related to quality checkout. Library modules have been created wherever possible, that there you can have the data. The diagram has a high fan in structure. Control modules have no more than 7 subordinates. Each module perform only one function, high cohesion. So try to, have this practically, but, in real, when you make a big, program or big system, then, try to avoid this, but we can't have always high cohesion. Sometimes it is moderate cohesion that, you have one or, couple of functions. Module sparingly share information, loose coupling. Data couple that are passed are actually used by accepting module. Control couples are passed from lower modules to higher modules, and each module has a reasonable amount of code associated with it. And after this, the third, so designing program. After this, program specification. No standard approach, including program information, note event that trigger action. List input and outputs include pseudocode, provide additional notes and comments as needed. So for example, sample pseudocode. Some of you might be doing some programming and that, calculate discount amount, total price discount amount. So if total price is less than 50, then discount amount is 0. Else, if total price is greater than less than 500, then discount amount, total price multiplied with 10%. Else, if the total price is less than 500, then 10% discount. Else, if it is more than 500 or more than 500, discount amount equal to total price multiplied by 20%. And if end. So basically you can clearly see this program. If price is less than $50, there is no discount. If price is more than, if price is less than $500, 10%. If price is more than 500 plus 500 or plus, it is 20%. So this is simple pseudocode. And sample program specification. For example, this, this is, I just make it bigger. You can see, okay, module here, for example, you are going to write the module name, fine tune by title. Purpose, display basic tune information using title input by user. Programmer is John Smith. Date due is this. What coding you are using: HTML, PMP, PHP, C, Visual Basic, or JavaScript. So basically JavaScript. What are the events? Search by the push button is clicked. Search by the hyperlink is selected. So these events are going to be created. Input name. So this is a typical form, and pseudocode is find tune module, not found tune. For all the tunes, titles is available. So basically this is like a pseudocode here. Other business rule: if no matching tunes are found, the artist of the week will appear to the user. So here this is the, if user title matches tune titles, serve tune ID. So basically this form you can see, this is sample program specification. It has all the information, including pseudocode is also here. So this is design part. We have one more chapter, which is chapter 11. And so let me show you the assignment related to this chapter. This is a mini case, So the mini case is this: common mistakes that normally you might make when you are doing the assignment of this week. Missing the loop control. So here you can see. And then incorrect loop scope. So here you can see, these are the common mistakes. So basically it's incorrect loop scope, common mistakes, a transform structure not well explained. So this is basically, you can do, it's a simple structure. Keep in mind, missing loop control, incorrect loop scope, these 4 things you can just, keep in mind, and you will be all right. So this is chapter number 10. So, do you want me to hold chapter 11? We don't have any assignment for chapter 11. So I will explain next week, which is the last class, next Tuesday. And so today only chapter 10, chapter 11 in last class, or you want to, we won't have the assignment. So you want to take a break for Thanksgiving, you can take. I will put the video, recorded class video. You have any question related to today's, or? Do you feel, you also have the power outage in your area yesterday, today? Okay, anyway, so this is what I wanted to talk to you today. If you have any question, I will be also available on Thursday. As usual, about 2 o'clock, 2:10 normally. If no question, I would like to say have a nice day, and hope you will have nice holidays of Thanksgiving time. So next class is optional. I mean, it's all up to you if you want to come. Okay, then I would like to, bye-bye, thank you.
Have a good day.
You too, bye.